Okay, so hello everyone. So we are here for our next Chemistry Olympiad training. In this lesson, we are going to be covering the basics of ionic and covalent bonding and using this as a basis to enrich our understanding. So let's start with set 7. Now, set 7 is a rather long set of notes, including ionic and covalent bonding. So let's quickly do a recap of ionic bonding as you have already learned this in class. First, ionic bonding exists between a metal and a non-metal when they react together to form ionic compounds. Now, why do you need a metal and a non-metal? You need a metal and a non-metal because metals will lose valence electrons. When you lose valence electrons, remember electrons are negative. If I lose the negativity, I lose negative charge, I become positive. All right. So loss of electrons forms positive ions. On the other hand, non-metal atoms, they will gain valence electrons and hence they form negative ions. So positive ions are also called cations, while negative ions are called anions. Okay, so cations means positive ion, anions means negative ion. Okay, so this is the role of the metal and the non-metal in the formation of an ionic compound. So if you are asked how is an ionic compound formed, an ionic compound is formed when metals lose valence electrons, non-metals gain valence electrons. Okay, another way to say lose and gain is a transfer of valence electron from the metal to the non-metal. All right. So transfer is another way of saying loss and gain of valence electrons. All right. Now, finally, now that you know that it forms positive ions from the metal, negative ions from the non-metal, the positive and negative ions clearly are attracted to each other, as you might expect, because positive and negative charges should attract each other. Now, this force of attraction has a name. It is just like how you learn in physics. Forces can be frictional force, gravitational force, and so on, right? So, the force of attraction between oppositely charged particles is called electrostatic forces of attraction. So, these are the strong electrostatic forces of attraction. What does electrostatic simply mean? Electrostatic means any positive charge attracting any negative charge. So like in the diagram below, the Mg2 plus ion attracts the Cl minus ion, and this attraction is called the strong electrostatic force of attraction between ions. Now at this juncture, whatever I'm saying right now has been covered in class. So one good way to study, of course, is to ask yourself, okay, do I really understand what is the meaning of electrostatic? Can I explain why metals lose valence electrons? Am I able to give an example of a metal that loses valence electrons? Can I explain why is it that when you lose valence electrons, it forms a positive charge? These are all questions that should come through your mind, and you should be conversant in explaining this. If you are unable to explain this orally, this means that you may not have mastered the concept as deeply as you think. All right? And this is what I mean by 15 minutes on just one page. Just this one page with 4 lines here can be a good 15-minute deep revision. Now, if you have revised deeply enough, the next question that is obvious to ask is, so does it matter whether it's 2 plus charge or whether it's 1 plus charge? How does the charge affect the strength of the force of attraction? Do you think Mg2 plus will attract Cl minus the same way as Na plus attracting Cl minus? These are all questions that you can ask yourself, and we are going to discover this later on this lesson. But even without a teacher teaching, this is one very good way to revise chemistry and to ensure that you have understood the concept before you move on. All right. So if you are wondering how you can spend 15 minutes per page, this is how you can spend 15 minutes per page and get a lot of it. Okay. So moving on. Now the next page shows you this crystal structure. This is a crystal structure of the compound magnesium oxide. Mg2 plus, O2 minus. The plus and minus balance out. So the formula is called MgO. MgO's name is called magnesium oxide. All right. So you can clearly see the Mg2 plus and the O2 minus ions are attracted. And what would you call this force of attraction? This force of attraction is called the strong electrostatic force of attraction between the Mg2 plus and O2 minus ions. Right? So every single line over there represents a strong electrostatic force of attraction between ions. Now, the next obvious question to ask yourself is, oh, MgO. MgO means I have one Mg2 plus, one O2 minus, right? That is the meaning of this formula. You have one of each. But is it realistic to say that the crystal of magnesium oxide only has one of each ion? Do you think ions are big or small? I think the answer is obvious, right? You have been taught that atoms are very, very small. Similarly, ions, which are formed when atoms lose or gain valence electrons, must also be very, very small. So the ions are very, very small. So clearly, your crystal of MgO cannot just have one Mg2 plus, right? So the idea is, it is not one Mg2 plus, one O2 minus. It is more correct to say that Mg2 plus and O2 minus are in a 1:1 ratio. Now that is different, right? 1:1 ratio can mean I have 1 million Mg2 plus and hence I have 1 million O2 minus. 1 million, 1 million is still 1:1. I could have 1 billion Mg2 plus, 1 billion O2 minus. It's still 1:1. So the idea behind chemical formula, as Miss Asma teaches you later on, is the idea that the ratio of the cation and anion is dictated by the chemical formula. So 1:1 means I have one portion of cation is to one portion of anion. They are in a 1:1 ratio. All right. Don't interpret it just simply as the number. All right. It's really the ratio. Now, how can we tell from this structure that it is indeed 1:1? Right? So one way is to count. You could easily count the blue dots, right? If you counted the blue dots, how many do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14. The blue dots are to represent Mg2 plus in this case, right? The blue dots are Mg2 plus. On the other hand, the green circles, which are slightly bigger, represent O2 minus. All right. How many O2 minus do you have? Count the green circles. If you count 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 13. Then you'll be like, oh, but 13:14 is not 1:1. Yeah. But remember, this is a giant ionic lattice. It goes on forever and ever and ever. Left, right, up, down. It goes on forever. I have only shown you a small segment of the lattice. Can I show you the whole lattice? I can't, because the lattice goes on forever. Right until the borders of the crystal. So many ions to show. There's no way I can show you the entire crystal. So within this sample, you can already tell the Mg2 plus and the O2 minus are approximately in a 1:1 ratio, which supports the chemical formula MgO. All right. Now, it is indeed 1:1. If you counted every single ion in the whole, it will eventually be 1:1. Having said that, we can only show you a small segment of the crystal here. So it is approximately 1:1. Hence, the formula is MgO. Now, how is this important? You realize that for pure chemistry, there are many questions like these. My fourth flourish students, you should be familiar with this by now, right? So, this is a common MCQ in pure chemistry. I've shown you the arrangement of the ions in an ionic crystal. Ionic crystal means ionic compound, right? So another way to say this is ionic lattice. All right. So which compound cannot have this arrangement of its ions? So again, you count. The black circle, the white circle, the black circle got 4, the white circle got 4. Oh, 1:1. That means the positive and negative ion has to be in a 1:1 ratio. Then it will fit this structure, right? Clearly, the one that's not 1:1 between the positive and negative ion is C. I'm sure you will agree. Okay, so C cannot have this arrangement because C is MgBr2. MgBr2 means Mg2 plus to Br minus is 1:2. A 1:2 ratio will not fit this arrangement. Okay, so the next one, I think my fourth flourish would have seen this before from our notes as well. So another very common question is, instead of giving you the structure, I give it to you in words, right? So the compound consists of a lattice of positive and negative ions. That's the ionic lattice. Now the next one is very important. Each positive ion is surrounded by 6 negative ions. What this means, one positive ion attracts 6 negative ions. On the other hand, each negative ion is surrounded by 3 positive ions. The negative ion attracts 3 positive ions. Oh, how am I going to solve this problem? So use common sense now. Replace the word surrounded by attracts. If I'm a positive ion, I attract 6 negative ions. But if you are the negative ion, you can only attract 3 positive ions. So what does this mean? Who is more attractive? Is the positive ion more strongly attractive? Or is the negative ion more strongly attractive? Which one is more? And I'm sure you'll come to the conclusion. The positive ion is more strongly attractive because it can attract more ions to itself, right? This means that it has a larger positive charge. The positive charge must be a bigger charge. And with that, I'm sure you can see positive, bigger charge, negative, not so big, smaller charge in this case. Clearly, A is wrong, C is wrong, right? Because in A and C, the positive charge is not larger. So the answer is either B or D. All right, where the positive charge is larger. So now you're going to decide whether it's B or D. How do you decide? We go back to the question. Chemical name, chemical name. Metal F is a chemical name. It's a metal. Metal means it has to form positive ions, meaning F should have a positive charge in its ion. And hence the answer is B. Metal F. Metal forms positive ion. So in this case, it has to be the one with the positive charge, while G has the negative charge because it's a non-metal. Okay? Please take note when we set these questions, F and G are not the chemical symbols of the elements. F is not fluorine in this case. F is a metal, an unknown metal. Okay? So any questions on these questions? So for my Sec 4s, I also sincerely hope this is a good revision for all of you. All right, this has come out for the O levels before. So you need to know how to practice and analyze the words in the MCQ. It could very well come out as part of a bigger question in the Olympiad about crystal lattices. Okay, if you have any questions, please feel free to ask in the Q&A function. All right, if not, we move on. Now, properties of ionic compounds. When we talk about properties, we are looking at things that can be measured, things that can be observed. So, for example, you can measure the melting and boiling points. So, ionic compounds with a giant ionic lattice structure have high melting and boiling points. How high is high? A high melting point, generally speaking, is defined as more than 500 degrees Celsius. It's not a rule, it's just a guideline to help you. All right. So generally speaking, something that has a melting point of higher than 500 degrees Celsius is considered high. So why is it that the melting point is so high for an ionic compound? Ionic compounds have high melting points because a lot of energy is needed to overcome the strong electrostatic forces of attraction between the positive and negative ions. All right. So this links back to KPT, right? In order to melt or boil something, energy is taken in, overcome the forces of attraction between particles. In this case, it's ionic compound. So these forces are strong electrostatic forces of attraction. Okay. Now, electrical conductivity. So this one is perhaps less familiar. If you think back to lower sec science, you had learned this. Something conducts electricity when the charges are free moving. So if you have charged particles that are free to flow, free to move, then it will conduct electricity. Electricity is the flow of charged particles. So in short, do you have charged particles in an ionic compound? The answer is yes. You have ions. Ions are charged. But the difference is in the solid state, the ions are held in fixed positions. You know that particles in a solid vibrate about fixed positions. They are not free to move. So the ions are the particles. Ions are particles in ionic compounds. So the ions are held in fixed positions by strong electrostatic forces of attraction. Therefore, in the solid state, the ions are not free to move to conduct electricity. We say that in the solid state, there are no mobile charge carriers. Mobile means free moving. Okay? So, how then do we make the ions free to move? If you think back to KPT, the answer is obvious. I could melt it. So the molten state is when you melt the ionic compound down at high temperature. So molten means melted at high temperature. So if I have molten ionic compounds, that means they are in the liquid state. Molten means liquid state. In the liquid state, the ions clearly will be free to move because they can slide past one another easily. Liquid state, right? Aqueous state means dissolved in water. The solvent is water. So aqueous means solvent is water. So if I dissolve it in water, similarly, the ions are free to move to conduct electricity. Okay? Now, these ones you must know. All right, these are things that you will definitely be doing as part of pure chemistry for the Sec 3s. Link back to KPT. So this is another good way to study. Like I said, 15 minutes. One box here is 15 minutes. But do you link back to KPT? If you didn't link back to KPT, that means you have not revised thoroughly and effectively. Whatever I said just now, do you realize a lot of it is KPT? Like vibrate about fixed position. Slide past one another easily. These are examples of phrases from KPT. Okay? Finally, the last property is solubility. Ionic compounds generally dissolve in water. They are mostly soluble in water. On the other hand, Because they are soluble in water, they will be insoluble in organic solvents like oil. Besides oil, we have learned some, right? We have learned hexane. We have learned dichloromethane. All right. Dichloromethane is an example of an organic solvent. So generally speaking, ionic compounds do not dissolve in dichloromethane. So for the sec 3s, you just had dichloromethane, right? So do you then think that caffeine is an ionic compound? If you think back, caffeine dissolves in dichloromethane. Caffeine doesn't really dissolve well in water. So this shows you that caffeine is the opposite of this. So caffeine is not an ionic compound. So when I talk like that, do you go back to your WA1, the database question to think? All right. Same for my fourth flourish. As I talk now, do you think back to your sec 3 days? Are these things that you have forgotten? If you have forgotten this, what's our action plan to catch up? Okay. So any questions at this stage about the physical properties of ionic compounds in terms of melting point, electrical conductivity, and solubility? No. Okay. Now the last one is what I said just now, right? Does it make a difference whether the charge is 2 plus or plus? Which one do you think will attract more strongly? I think the answer is obvious, right? Okay. A doubly positive ion clearly will have a stronger attraction. Okay. Now, can we quantify this attraction? The answer is yes. The strength of the ionic bond, the strength of the electrostatic force of attraction is given by the lattice energy of the compound. Lattice energy is just a term. All right. The definition of lattice energy is just a definition. But essentially, lattice energy reflects, tells you the strength of the ionic bond. And guess what? The lattice energy is proportional to, this is the proportionality sign, the product of the magnitude of the charges over the sum of the radius of the two ions. Okay, so the charge you multiply together, but the keyword here is magnitude. Why do I stress magnitude? I stress magnitude because if it's MgO, O2 minus Mg2 plus, the charge is 2 plus and 2 minus, right? So what do I multiply? I will multiply 2 times 2. I don't want the plus, I don't want the minus. I just take the magnitude. Magnitude means just the number over the sum of the radius, okay? Whatever the radius is. Now, the radius of ions can be found online. All right? Can? So, it's obvious. If you look at this mathematical relationship, it's obvious, right? If the charge is larger, that means it's like 2 plus or 2 minus or 3 plus, 3 minus. So long as the magnitude of the charge is larger, the lattice energy will also be larger in magnitude. Right? Charge go up, lattice energy go up. Lattice energy go up, ionic bond stronger. Right? If the ionic bond, the electrostatic force of attraction is stronger, the melting point also go up. Okay? So that is an example. Okay? Now, lattice energy, this formula, in case you're wondering, if we take physics, if you study A-level physics, this is actually the starting of what you call electric potential energy. The formula that I've just given you is a simplified formula for electric potential energy. So you have learned formula for, let's say, gravitational potential energy. Electric potential energy also has its own formula. In case you're wondering, Okay, it's a very complicated formula, but you can start to realize some similarities, right? Q1, Q2 means two charges times together. 4, I'm sure you know what's 4. Pi, I'm sure you know what's pi. This one is weird, this read as epsilon naught. It's not 0, When you see 0 at the bottom, it's always written as naught. Epsilon naught is how you pronounce it. Okay? But the actual name of this term is called permittivity of free space. The permittivity of free space literally means in a free space, how long does a charge exert its influence, its force? Okay? It's a constant. Permittivity of free space is a constant. And finally, R is radius, right? In this case, hello, positive, negative, so the combine, the sum of the radius. That's why you can see the radius add together. All right. So this is the formula for electric potential energy, which is the form of potential energy you have when you have charged particles attracting or actually repelling each other as well. Okay. And so I finished ionic bonding. At least I finished some of the ionic bonding. Okay. Now it's time to toggle over to set A. All right. So now let's flip to the back of this set where you'll find set A. Now, set A is a good introduction to the concept of radius. What on earth does it mean radius? Just now I said, right, the radii of atoms and ions can easily be Googled online, found online. Okay. But how on earth do we even define the radius? Well, a good way to define the radius is simply to imagine our atoms and ions as circular, right? If we imagine the ions to be circular, then it's easy, right? Radius just means the center all the way to the outermost, lah. Right? That's radius, what? Am I wrong? Radius is the center to the outermost boundary, right, of the circle. That's radius. So now let's relate this to our atoms and ions. Outermost what? What's this thing? Outermost shell. Do you realize now? The radius of an atom, very simply put, could very well be the distance from the center of the nucleus to the valence electron shell. That is the radius of the atom. Which is to say, if an atom has more and more shells, the radius should become larger. Okay? Now, that is the most simplistic form of thinking about atomic and ionic radius from the nucleus to wherever the valence shell is. But we may need to be more sophisticated. Why so? We have different materials with different types of bondings. Remember, our substances don't exist as just one atom, right? They can be bonded together. So depending on the type of bonding, you will realize that the measurement of this radius changes slightly. Okay, so for example, I've shown you here metallic radius, covalent radius, and finally the last one is called van der Waals radius. Now, I would like to pay attention to the van der Waals radius for now. Now, the van der Waals radius of an atom refers to half of the internuclear distance. Whoa, nucleus, nucleus, internuclear distance. All right. So this is called the internuclear distance. All right. The distance between two nuclei of two atoms. Importantly, in the van der Waals radius, the atoms are not covalently bonded together. They're not interacting. Okay? And I'm sure you can imagine half the number, half times the distance that I've shown in the red arrow. Okay? Now, why do I want to focus on the van der Waals radius? You notice the van der Waals radius is defined rather oddly. It's defined in terms of not chemically bonded, they are not interacting. Because of this, if they are not bonded, another way of saying not bonded means not attracted. They are not attracted to each other. I'm not sure if you realize a force of attraction is a form of bonding. It's a form of interaction. So not chemically bonded means not attracted to each other. So imagine if they are not attracted to each other, would you expect the distance to be larger? Are they further apart? Or do you expect the distance to be closer? I think it's obvious, right? If they are not attracted, it's just like maybe you and your friend. If you are not very good friends, you're not very close to each other, you literally won't sit close to each other. Same here. The atoms are not chemically bonded, they're not attracted, and therefore you expect the van der Waals radius to be the largest of the three definitions. That means comparing the van der Waals radius with the metallic radius or the covalent radius, the van der Waals radius is the largest. It is the largest because it represents the radius in terms of the internuclear distance between two atoms that are not chemically bonded. Okay? Now, why am I going through this? This is a very typical database question. All right, where they give you the three definitions and ask you, suggest a reason why the van der Waals radius is larger than the metallic or covalent radius. And this is the answer. This is because the van der Waals radius is defined in terms of half the internuclear distance between two atoms which are not chemically bonded, meaning they are not attracted to each other, hence it's the largest. Okay. Now, we need to settle these definitions of what is an atomic radius first before we can move on. I hope you realize right now, atomic radius can really be defined in many ways. And why so many ways? Because you have different sorts of bonding in different sorts of materials. Metals obviously use the metallic radius. Covalent radius, as you will learn later for the Sec 3s, is when you have covalent bonding, and that happens for non-metals and non-metals. Okay? Now, does to the questions that have appeared in the Q&A button, does this mean that the atomic radius is the distance from the nucleus to the valence shell, or the distance between one proton to one electron in the outermost shell? The answer to this is the atomic radius is defined as the distance between the center of the nucleus to where the valence shell is. So from the center of the nucleus to the valence shell. Next, which radius should we use to define the true size of an atom? And the answer is all of them and none of them. Okay, this sounds very sophisticated. What do you mean all of them? All of them are equally valid interpretations of what the radius is. But are they all accurate 100%? No, they are not. Right? So remember in lower sec, we taught you this is the model of an atom. Same here. This is the model of what we think the radius is. So the answer is all three of them here are models of what atomic and ionic radii are. Why is it half? Why half? Hello, radius. This distance is a diameter. Radius is half of a diameter, right? Remember radius. Okay, must have it. Radius is always halved, okay? All right. So it's the same as circles, right? The whole distance is a diameter. So for example, if Mr. So draw two circles touching each other, what's the radius? Is this the radius? No, it's not. It's the diameter, right? The radius is just half of that. Okay, why don't we just use one atom though? That's a good question. And the answer is substances don't just contain one atom. it's very, very difficult. It's possible, but it's very, very difficult to just take one atom and look at it. It's very difficult experimentally. Okay, and that's why we need to actually use a sample of atoms. So you can imagine that actually we don't just take two. Probably in the actual experimental sense, you take one row of atoms, and that's already a very small number. You know? Can you imagine one row of atoms, only 100 atoms, let's say? That's a very small number. I cannot imagine just having 100 atoms. In a typical substance, you have like millions and billions of atoms. All right. Now, after we have understood what atomic radius is, what's more important is to understand the trend in the atomic radius and ionic radius across a period. So let's start with atomic radius. Atomic means what? Atomic means atom. Atom means what? Atom means, has it lost electron? Has it gained electron? No. Atom means from periodic table, haven't lose, hasn't gained. Meaning sodium atom is 281. Haven't lose the 1 yet. Magnesium 282. Aluminium 283, and so on and so forth. All right. Now, it might surprise you that atomic radius decreases, right? I'm sure you can see atomic radius decreases. At least from sodium to chlorine, it decreases, which might come as a shock. Aren't they all in period 3? Don't they all have 3 shells? If they have 3 shells, shouldn't the distance from the nucleus to the valence shell be the same? So why should the radius decrease and become smaller as you go from left to right? And this, we need to think harder. Remember, atomic radius is from the nucleus to the valence shell, right? Where is the valence shell? Oh, the valence shell is the third shell, cause period 3. Correct. For period 3, the valence shell is the third shell. But do you seriously think the third shell electrons are equally attracted to the nucleus? What can you say as you go from sodium to chlorine? As you go from sodium to chlorine, you literally go from 11, 12, 13, 14, 15, 16, 17, right? What I just read out is the number of protons. As you go from left to right across any period, the number of protons increases. You have more and more protons. How is this significant? Now, this is significant because, remember, the valence electrons are attracted to protons in the nucleus. If you have more protons, the valence electrons, before that, not only do you have more protons, but the number of shells remains the same. So I keep the number of shells the same, but I got more protons. More protons to do what? More protons to attract the valence electrons. So the valence electrons are more strongly attracted to protons. Ooh, okay, my handwriting, I'm so sorry. Protons in the nucleus. Okay, I'm sure this one you will agree, number of protons, number of shells, valence electrons more strongly attracted. I'm sure you will agree with this. Right? It's a clear logic, follows what you might expect. Okay? Now, if the valence electrons are more strongly attracted, what do you expect the valence shell to do? If it's more strongly attracted, we said just now, right? More strongly attracted, it will go closer and closer, nearer and nearer. If it's not strongly attracted, it will be further away. Hence, the atomic radius should decrease because the valence shell compacts and is attracted inwards. Okay? So it's always about number of protons and how strongly attracted the valence electrons are to the protons in the nucleus. So there are a few questions that have come in. So does it matter the number of valence electrons? Does the number of valence electrons also affect how strongly attracted it is to the protons in the nucleus? And the answer is No, it doesn't. Because electrons in the same shell do not decrease the attraction felt by the valence electrons to the protons. If they are in the same shell, they do not affect each other in terms of attraction. All right. Okay, we are not on transition metals yet. So now we are at period 3. Period 3. We are not touching transition metals today. To answer transition metals, that's more complicated. Learn period 3 first. All right. But the transition metal question is good. We have one session on transition metal later on, but we'll come back to that. But learn period 3 first. By the way, period 3, no transition metal. Look at periodic table. Sodium, magnesium, aluminium. That one, no transition metal. Period 3. In case you're wondering, what on earth? Why on earth do we say period 3? Like, isn't like other numbers more auspicious, like period 8 or period 6, 7, like you always say 6, 7, right? No, period 3 is a good period because these are common elements, right? Sodium, magnesium, aluminium, chlorine. Okay, is this a common trend that can be tested under periodic table chapter 14? I guess it's from Fall Flourish. Yes. All right. Now, of course, the obvious elephant in the room is argon. Okay, it's odd. It doesn't seem to follow this trend from sodium to chlorine. There must be a reason why it's an exception. So I think my Fall Flourish students have written in their study tips, whenever there's an exception to the trend, must learn also, okay? Yeah, must learn. Now, argon is an exception to the trend. And the reason for it must have something to do with argon. So ask yourself, in an exam, ask yourself, how is argon different from all the rest? Well, I'm sure you can come to the conclusion. Argon is a noble gas, right? What can you say about noble gas? Noble gases are unreactive. I'm sure you know that. Why are they unreactive? They have fully filled outermost shell. This one I'm sure you know. Okay, so this is what you memorized, you learnt. But let's put this into practice. So if it's unreactive, means it does not bond to other elements or even to other atoms of itself, right? It doesn't form bonds, full stop, period. Because it's unreactive, it has a fully filled outermost shell, there is no need to lose, gain, or share any more valence electrons. Oh, doesn't bond. I thought I just heard this a while ago. Not bonded. Not chemically bonded means, oh my god, do you think argon has a covalent radius? No. Does it have a metallic radius? Even more no, because it's not metallic. So argon only has the van der Waals radius. And what did we just say about the van der Waals radius? It's not chemically bonded, right? So the van der Waals radius is always larger than the rest. So for the other elements there, they either use the metallic radius for the metals or the covalent radius for the non-metals. Okay? But for argon, you can't use metallic because it's not metal. You can't use covalent radius because it doesn't bond. So the only radius you can use is van der Waals. And we just said van der Waals radius will be larger than the other two. That's why argon is a exception. Okay? Of course, some of you will be thinking, oh, is this a possible database question? The answer is, of course, yes. I've seen other schools set this before. The whole question was about van der Waals radius, metallic radius, covalent radius, and the trend. Okay? So yes, it has been said before. It's not very creative anymore, but since I've told you that, let's learn it, okay? Do all the group 18 elements, meaning the noble gases, follow this van der Waals radius? That means do all group 18 elements only have van der Waals radius? And the answer is yes. 18 elements only have the van der Waals radius. Okay, for my fourth flourish, I think this is also new. So hopefully you can have a think about it. See how you can link this to some of the chapters like periodic table that we have done before. You can think about bonding. Oh my god, this is a great question for bonding, periodic table to all crash together, right? Yeah, sounds great to me. Okay, that's atomic radius. Atomic, atom, what's atom? Atom means from periodic table, take out. Oh, 281 is atom. Okay, hasn't lost electrons, hasn't gained electrons yet. So now let's move to the next one. Of course, after atom, we should talk about ion. This one is the one where I feel many students are not very, very careful. I've tried to help all of you by giving you the charges already. Let's ignore the Si4 plus. This is very theoretical, probably. Okay, in case you're wondering, does silicon really form Si4 plus? There's no compound of silicon that I know that has Si4 plus ions. Silicon group 14 generally will form covalent bonds. They don't form ionic bonds generally. So this is probably a theoretical answer. In case you're wondering what is theoretical, theoretical means you do mathematics, work out equations, sub in values, and then you get an answer. All right. And the equation is what you saw just now. The equation that I've given you. Okay. I hope we know metals form positive ions. So Na plus, Mg2 plus, Al3 plus. Yep. So let's be very careful. Okay. Na is 281. Na plus is 28. So Na plus is 28. Okay. Now I'm sure you know by now, Mg2 plus is also 28. Al3 plus is also 28. Okay. But the question is Cl minus also 28? Cl is 287. So Cl minus is 288 because it gains electrons, right? Immediately be like, oh wow, so it's different? Yes, it's different, right? Clearly it's different. Cl minus is 288. And that's why for the 3 flourish, how do you do the last MCQ of your WA1 quickly? The idea is, if they are in the same period, can they have the same electronic configuration if they are positive and negative ions? Do the positive and negative ions in the same period look like they even have the same electronic configuration? The answer is no, right? If they are in the same period, the positive ions have one less shell compared to the negative ions. I repeat, if they are from the same period, the positive ions will always have one less shell. This means they can't have the same electronic configuration. The ions from the same period do not have the same electronic configuration. The positive ions is one electronic configuration, the negative ions is a different electronic configuration. And that is how you work out the MCQ for the last question of your WA1 for the 3 flourish very quickly. You can eliminate so many possibilities immediately instead of working each and every one out. Same period, positive, negative ions will never have the same electronic configuration. Besides that, same group also will never have the same electronic configuration. Imagine group 1, 281, 28881. How on earth will the same group have the same electronic configuration? Cannot. Okay? So for the 3 flourish students, I hope you learn this is one trick in doing MCQs fast. Okay, if you recognize patterns like that, it's much faster. Now for the 4 flourish, what I'm talking about is, do you realize same period, the ions do not have the same electronic configuration? I hope you do. Now, how is this even important? This is super important because what can you say? The first thing you can say is cations from the same period. And remember, cations are formed when metals lose valence electrons. So the cations from the same period, the positive ions, formed when the metals lose valence electrons, have a smaller much smaller actually, radius than the anions which are formed when non-metals gain valence electrons, right? The positive ions are much, much smaller. Okay, for Paul Flourish, this was formative assessment for question 4. Okay. Now, what's the reason for this? You must explain, right? Chemistry is all about explaining. So the reason for this is cations have one less shell than anions, right? The cations are all 2-8. The anions are all 2-8-8. So the cations have one less shell. And they have one less shell because metals lose valence electrons when forming ions. Okay. Okay, so I'm going to give you some time to take this down, internalize it. Now, so you notice, Mr. So literally, okay, when I describe a graph, I will describe the bigger trend first. Bigger trend means what? The bigger trend obviously is the difference between the anions and cations. There's a big difference, right? So if there's a big difference, I will start off by describing the big difference first. Always have this structured thought process. When you look at a graph, always go for the bigger trend first. The bigger increase first, the bigger decrease first. In this case, the bigger difference first. All right. Of course, once you are done with the bigger trend, the next one is to focus on the individual smaller trends. So are there smaller trends? Do you notice I've used two colors to highlight? One color in blue for the cations, another color in yellow for the anions. Why do I do that? It is to show me visually that, hey, amongst the cations, it decreases as it goes from left to right. Amongst the anions, it increases as it goes from left to right. So that is what I now need to do. Okay? Okay? Can? So now the individual trends. And how do I describe it in words? As we move from left to right across the cations, Na plus to Al3 plus. So this is how we express it as we move from left to right across the period, left to right across cations, and also across the anions, right? P3 minus to Cl minus. Do you realize the ionic radius or radii, because it's plural, decrease within each series? There are two series here, right? Cation and ion. Within each series, the ionic radii decreases. So again, what's the reason? So now you cannot use the shell reason, right? Cation, Na plus, Mg2 plus, Al3 plus, they all 2-8, all two shell. Same number of shell already. So what's the difference? The difference is no longer the shell. Remember, in chemistry, the why, the reason is always to do with how are these things different? How is Na plus different from Mg2 plus, from Al3 plus? And the answer is the same as what you learned just now for atomic radius. As you move from left to right across a period, the number of protons increases while the number of shells remains the same within each series. I keep saying within each series. I'm comparing cation with cation, anion with anion, right? Okay. So what does this entail? This means the valence electrons are more strongly attracted to protons in the nucleus. Okay, within each series, the valence electrons will become more strongly attracted to the protons in the nucleus. So, for example, Al3 plus, the valence electrons in Al3 plus are more strongly attracted to the protons in the nucleus than Na plus. Cl minus, the valence electrons are more strongly attracted to the protons in the nucleus compared to P3 minus. Comparing cation with cation, anion with anion can only compare within the series, okay? Not across cation and anion. Okay? Now, this is what typically you will learn at A-level H2 Chem when you start the topic of periodic table in H2 Chem. Now, for my fourth flourish students, I hope you realize by now, the same explanation, number of protons increases, number of shell remain the same, the valence electron become more strongly attracted to the nucleus. This explanation literally is repeated again and again across so many different things. Okay, so another study skill that you need to have is to recognize patterns. If you recognize that the same explanation has been repeated so many times, it means that this is a key concept. You need to understand it well. All right? Okay, so right now the time is 6:20. Are we doing good? Do we understand an ionic radius? Okay, so does a Na plus ion have the same radius regardless of its crystal structure? So let's say, okay, if it bonded to something else, let's say sodium chloride compared to, let's say, sodium oxide, does the Na plus ion have the same radius? The answer is, I have no reason to think that it will have a different radius. Okay, so the ionic radius should remain the same. Okay, having said that, that's a very theoretical answer. I think in actual fact, if you actually want to experimentally go and find out the radius, there might be slight differences, but the slight differences probably will be within the experimental error margins. Okay, but there are some exceptions. But the exceptions, let's get there later. Okay, that's what happens when the ionic radius will change when you start dissolving stuff in water. So whatever I've just done so far, ionic radius, I'm literally talking about the ionic radius in, let's say, the solid state or the gaseous state. It's either solid or gaseous state. Okay, these are easier to describe. The moment you start dissolving something in water, for example, if you dissolve sodium chloride in water, the ionic radius of Na plus might change because it starts attracting water molecules around it. All right, so the ionic radius that you can measure in water in aqueous state can be different. But that's a different concept, okay? That one you need a lot more chemistry and a lot more physics to understand it. All right? Okay, next, we should move on in set 8. I want to end off with this. All right? Now, we are not going to get on to covalent bonding today, given the time. I think we can get on to this. I hope my fourth flourish, you recognized this diagram because I went through this in chapter 4 enrichment last year. Let's see whether fourth flourish, do you recognize this? Response please, fourth flourish. Some response please, fourth flourish. Do we recognize this at all? Two people have responded. One more thinking. Yeah, you recognize this, right? Beyond the graph, which is of course mathematics, I think what's more important is let's understand how covalent bonding works. Now, for 3 flourish, probably you will start covalent bonding in term 2. All right, it's fine. Okay, covalent bonding is when two non-metal atoms come together to share valence electrons. So far you have done losing, gaining, but there's a third way. The third way is to share valence electrons. So for example, if I have two non-metal atoms, both are non-metals, both wants to gain valence electrons. That's not possible, right? You can't have both gaining valence electrons and no one is losing valence electrons. So if both want to gain, then how? Well, the answer is very simple. Right? So let's say, I always use this analogy in class. Let's say you wanted to buy pizza. Pizza costs $20. What if, let's say, Teng Zhi, you have $10. Mr. So has $10. Can we individually buy the pizza? There's $20. The answer is no, not enough money, right? We need more money in order to afford the pizza, right? So what happens? Both of us need more money, you know, just like how two non-metal atoms, both of them need more electrons. Then how? So the answer is, how about Teng Zhi and I can share the money, pool the money together. So now his $10 and $10 becomes our common shared property. If we have common shared property, we now have $20 between the two of us. Now we can share the money to buy the pizza. Then we can share the pizza together. So the idea is sharing. Covalent bonding is all about sharing of valence electrons. Okay? So then how are the valence electrons going to be shared? Obviously, the atoms must come together. If they don't come close to each other, like how on earth will the electrons even get to interact and be shared, right? So this graph that's very complicated describes to you what happens when the atoms start coming closer and closer to each other. This is literally how covalent bonds are formed. Now, whenever you have a complicated graph, please start somewhere. Don't like anyhow read. Whenever there's a graph, always look at the axis. My y-axis is potential energy. My x-axis is distance between atoms. Okay. Now, at O-level physics, you do not learn negative values of energy. I repeat, at O-level physics, you do not learn negative values of energy. So right now, you will need to take it from me. 0 is over here. Anything below 0 is negative. Okay, we know that. Below 0 means negative. Negative potential energy refers to attraction. Okay, negative potential energy refers to attraction. Okay, now does this only apply to electrons? No, it doesn't. All right, in fact, shockingly, but please don't use this at O level. When you learn gravitational potential energy at A level, you will learn a new formula for gravitational potential energy. Gravitational potential energy is actually negative. All right. So it is not exactly right to say I have 100 joules of GPE. No, it's not correct actually. Technically, it's not correct. Okay? Because you are actually attracted to the Earth, right? You are attracted by the Earth's gravitational field, right? So because it's attraction and gravitational force is always attraction, so actually gravitational potential energy is defined to be negative. Okay? Now, does this mean that energy is a vector for those physics students? No, energy is not a vector. Energy is not a vector. Doesn't have direction. All right? It's negative because how we define 0. I repeat, attraction is negative because of how we defined 0 energy. Now, this 0 energy is a rather strange concept. Why would two things have 0 energy between them? And the answer is simple. Two things have 0 energy between them if there is no attraction. If they are not interacting at all, I don't attract you, neither do I repel you. we are totally unrelated. We are not interacting. If I'm not interacting with you at all, our energy of the interaction is zero. Right? So, for example, let's say, but please don't do this, but let's say you decided to ignore your friend for a day. Ignoring, our interaction is zero. If our interaction is zero, our energy is zero. There's nothing happening between us. Okay? So, same here. We define zero energy as the point where the two atoms and their electrons have absolutely no interaction whatsoever with each other. Okay? Can? So I haven't started reading the graph. I'm still at defining what is zero energy. Okay? So zero energy means no interaction. Why do they not interact? They do not interact when the atoms are very far away from each other. May I know what's very far away? Very far away means the distance equals infinity. The distance equals infinity. That's called very, very, very far away. Okay. Next question. Can you ever reach infinity in mathematics? I'm sure you know the answer is no. Right? You can't reach infinity distance, right? You can't reach infinity, right? Which is why, can you see this dotted line where energy equals to zero? This dotted line is the asymptote to the graph. I think you know what is an asymptote. An asymptote means it's a line that the curve will never ever cross. It goes near to this line. The energy can go near to zero. All right, but it will not cross it. They'll be like, oh, what? But didn't you just cross it here? That's a different story later on. Okay, but you can see that it's going near to the line, but it doesn't cross it. Okay, but this point on the left is a different point. It's a different story. Okay, so far we have finished box number 1. When the two atoms are very far away, the attraction is negligible. Therefore, the energy is zero. Oh, by the way, yes, asymptote exists in many functions. Y equals to 1 over x has an asymptote. Y equals to 1 over x squared has an asymptote. Y equals to e to the power of x has an asymptote. Oh my gosh, wow. Y equals to ln x has an asymptote too. Yeah, so the analogy is right. That means if you and your friend are strangers, you do not interact at all, the energy is zero. Okay? So it's like the atoms are totally strangers. They do not interact. Okay? Now that's box number 1. Of course. Now what happens if I make the atoms come closer to each other? As the atoms come closer to each other, obviously they interact. The electrons, the protons will interact. How do they interact? As the two atoms come closer together, the protons in their nucleus will start attracting the electrons from the other atom. It's like you seeing your friend from far away. Hey, come over. It's the same concept. All right. So same here. The protons in the nucleus of an atom can start attracting the electrons from the other atom. Okay. Now, attraction decreases the energy. I repeat, attraction decreases the energy of the two atom system. Okay? Can? Now, for the fourth flourish, I hope you know by now, a decrease in energy. Bond formation. Now you know why bond forming, right? Attraction means forming bond. Oh wow, so bond forming means the energy go down. Oh, energy go down means energy is lost to the surroundings. That's why bond forming is exothermic. Yes, for flourish. Yes. So now do we appreciate one more viewpoint? Oh my god. They start attracting. Attracting means forming bond. Forming bond means the energy go down. Energy go down means energy is given out to the surrounding. So bond forming equals give out energy equals exothermic. And this is the graph to show that. Okay, for flourish. Yeah. So when you form bonds, when you attract, the energy goes down and energy is given out. Okay. Now something else you need to learn, and this one you need to learn. When energy goes down, it means that the system becomes more stable. Okay. This is an important central concept throughout physics and chemistry. Energy is a very important concept because if the total energy, okay, the total energy of the universe is conserved. But in this case, if I just look at the two atoms, if the energy of the two atoms goes down, it makes the two atom system more stable. All right. So when energy goes down, the lower the energy, the more stable the system is. So as it's attracting each other, it becomes more stable. Does that make sense? It makes sense, right? You already learned what? Uh, Things like atoms, they want to lose, gain, or share valence electrons so that they achieve a fully filled outermost electron shell, which is also called stable noble gas electronic configuration. Right? Make sense? So you have written stable noble gas electronic configuration so many times. Did you realize that? Oh my god. So that means when they lose, gain, or share valence electrons and bond to other things, importantly bond to other things, they become more stable? Yeah. So that's why we bond. When we bond to other things, we become more stable. The only exception is noble gases. Oh, why noble gas is the exception? Because noble gas, they already got fully filled outermost electron shell. They don't need to bond. But for everything else, I am sodium, you are chlorine. I lose, you gain. Together we bond together, stable. Or I am hydrogen, you are hydrogen. We share, stable. Okay? So when we say something becomes more stable, it means the energy goes down. Of course, will the energy go down forever and ever? No lah. Okay, there's a minimum point. Okay, there's a minimum point. Minimum what? Minimum potential energy. When the potential energy is at a minimum, the system is most stable. All right. For the four flourish students, I presume learn how to find a minimum point using differentiation. So imagine if you had the equation of this graph, you could perform differentiation to find at which value of distance is the energy the minimum. And that is how we use differentiation in science. Okay, personally, I have done this before. All right. I mean, I know the equation, so I can actually differentiate the equation to work out theoretically where is the minimum point. By working out theoretically where the minimum point is and the coordinates of the minimum point using differentiation, I can work out the length of the covalent bond. Okay. Now, so the system is more stable when the energy is at a minimum, meaning, oh, so at this length, at this particular distance, this is the equilibrium bond length. That means the covalent bond, the length of the covalent bond is that. Obviously, they share electron. After sharing, they want to be stable, right? So the most stable point is where it goes, lor. It will go to the most stable point, stay there. That's the equilibrium. Okay? So equilibrium means good, right? Now, for the three flourish pure physics students, Mr. Song literally just did equilibrium with all of you. Oh my god, when do you learn this word equilibrium in physics, everyone? We learned it under Newton's first law. So equilibrium exists when forces are balanced and there's no resultant force. Why would there be no resultant force? Okay, so let's examine. If I draw two atoms, they attract. Attraction, right? Fa, attraction. The proton attract the electron from the other atom, right? But similarly, are you sure it's just attraction throughout? You mean They attract the electron, but you mean they don't repel the proton from the other atom, man? It's the same one. Oh, I enjoy being with my friend because my friend is fun. My friend will help me in mathematics. I like these parts of my friend. But are you sure you like everything about your friends? Maybe sometimes you also don't like the fact that they're very talkative, very noisy, distracting. Same here, right? The proton attract the electron. You're so sure the proton won't repel the proton? Exactly. So besides having attractive force, there is also repulsion. There's repulsion between the protons of the two atoms. Okay? So the equilibrium occurs when the attraction of the proton with the electron is equal to the repulsion of the proton with the proton of the other atom. And that results in a no resultant force on the atom. Hence, the forces are balanced and so it reaches equilibrium. Okay, of course, for those non-physics students, this is just extra info. For the physics students, this is one good way to study, right? You can link chemistry to physics. How wonderful, right? Okay, so of course, all good things must come to an end. Like my lesson must come to an end. So how does my lesson come to an end? My lesson comes to an end when you force the atoms to come even nearer and nearer and nearer to each other. Oh my god, they're already at equilibrium, but you're still not happy. Let's say I go and force them to come closer together. Oh my god, they force them to come closer together, what happened? If you force them to come closer together, imagine the atoms are literally squeezed like you know, tuna in a can, they're squeezed together. If they're squeezed together, it means the protons are so near each other now, the protons of one atom will start to repel the protons of the other atom so much. So meaning the repulsion force is bigger than the attraction force. So now the resultant, the overall sum of the forces, will be more repulsion than attraction. And that is exactly what's happening when the graph shoots up. When the graph shoots up, it's repulsion. So all this is repulsion. When the graph goes up, when potential energy goes up, okay, it's repulsion. All right. And why is that repulsion? It's because now the atoms are so near each other, the protons are so close to each other, they start to repel each other so much. Okay, so I said so much. You must be wondering, oh my god, how much math and physics is there? Well, chemistry is the middle central science. There will be some topics I talk about later on. For example, in about 2-3 weeks' time, we're going to do organic chem together. And when we do organic chem together, I'll talk about cortisol. We have now this cortisol movement, right? Wow, you like to talk about cortisol. Okay, but cortisol is an organic compound. So chemistry is very linked to biology as well. Especially when we talk about organic chem later on, I'll say a lot about biology, cortisol. What is cortisol, right? But at the same time, chemistry is very linked to physics as well. Okay, that's why chemistry is the central science. That makes it interesting and difficult. Okay, so if you don't take physics, don't worry. But do you have in your brain the idea of attraction and repulsion? Do you know that protons and electrons attract while protons and protons repel? If you have that in your brain, you will understand this. Okay? Now, okay, so I think I've covered the Lennard-Jones potential to answer the question on differentiation. How do you know how to differentiate this? It's not difficult because there's a formula for this. I'm trying to remember the formula. Give me a while. Um, okay, the A and the B the A and the B are just constants, which you can actually find out through doing some clever assumptions about what the molecules are like. So what happens is that there's a negative term. The negative term is the attraction term, and the positive term, as you can see, is positive means it's repulsion. Okay, so I'm sure you can differentiate this now. By now, for flourish, you should be able to dy dx this, not dy dx, but dv dr this. Yes. Okay, So to answer the questions, let me answer the questions after I stop the recording, okay? But that brings us to the end of today's lesson. For those in the Google Meet, I suggest you stay a while so they can listen to my answers to the question. If not, thank you very much. Let me stop the recording first.